So we're going to pick up where we left off on Friday, and you will recall that we were talking about the conformations and the energy of ethane and propane, and we ended with a quick glimpse at the energy diagram of butane. And so, just to refresh and review here, when we look at the different conformations of ethane, ethane only has two carbon atoms. And the two carbon atoms in ethane are those that are utilized in the Newman projection in the front and the back there, those two atoms. And attached to each carbon atom is three hydrogens. And so in ethane here, we see that there are really only two different conformations as we spin those H atoms around in a circle. We have the all eclipsed conformation, where every hydrogen atom is eclipsed with every other hydrogen atom. And we have the all staggered conformation, where all the hydrogen atoms are staggered with a dihedral angle of 60 degrees. So these just keep repeating again and again, and the difference in energy between those two conformations is 3 kilocalories per mole. When we look at the different conformations of propane, we see a similar kind of pattern where one of those hydrogen atoms, it has been changed for a methyl group, a CH3 group, and so rather than having three different groups of hydrogen atoms being eclipsed, now we have two groups of hydrogen atoms being eclipsed and a methyl eclipsing a hydrogen in the all eclipsed conformation at 0 degrees. And when we're at 60 degrees, we see that we have an interaction with a methyl group being 60 degrees away from a hydrogen on either side. And as we spin these groups around in a circle, changing the dihedral angle by 60-degree increments, we see that, again, these two different conformations are just repeated over and over again. Every eclipsed conformation that we can form is exactly the same as all the other eclipsed conformations that we have already formed. Namely, that there are two interactions of hydrogen atoms, two pairs of hydrogen atoms eclipsing, and a methyl and a hydrogen atom eclipsing. And every staggered conformation is exactly the same as every other staggered conformation. So these just keep repeating again and again. And here we can see that the energy difference between these two conformations is 3.3 kilocalories per mole. So a little bit higher than ethane, where the energy barrier there was 3 kilocalories per mole. Finally, when we get to something like butane, we see that now there's actually different energies involved. We're not just cycling between the same two energies over and over again, eclipse staggered, eclipse staggered. Now we have different energies for different eclipsed conformations. There are two different eclipsed conformations, and there are two different staggered conformations. And so we create a pattern. The potential energy diagram looks a bit different here. We can see that at 0 degrees on the far left, we have a syn interaction where there's a 0-degree dihedral angle between those two methyl groups. So those two CH3 groups on top have a 0-degree interaction, which means that they're very close to each other. That is the highest energy conformation in butane, and we can see on the far right that same conformation is repeated at 360 degrees. So the highest peak on this potential energy diagram comes from the interaction of those two methyl groups in that eclipse conformation. And also in that conformation, we see that there's two pairs of hydrogen atoms that are also eclipsed. As we rotate the front carbon atom 60 degrees clockwise relative to the back carbon atom, we can see that the dihedral angle has increased from 0 degrees to 60 degrees. And that's what we call a gauche interaction. When we have two methyl groups that are 60 degrees apart, we call that gauche. And you can see that that's substantially more stable than the syn eclipsed conformation that we just came from. The energy has dropped substantially. We're not quite at the bottom yet. It's not as low in energy as the 180-degree conformation, but it is still much lower than what came before. And as we rotate again 60 degrees clockwise, we notice now that we come to another eclipsed conformation. Notice that the conformations always go eclipsed, staggered, eclipsed, staggered, eclipsed, staggered, because we're always moving in those same 60-degree increments. So here, when we're at 120 degrees between those two methyl groups, you'll notice that there are two different eclipsing interactions containing a methyl group and a hydrogen atom. So methyl hydrogen, And then the last eclipsing interaction is hydrogen-hydrogen. So that's another eclipsed conformation. So again, higher in energy than the staggered conformation we just came from, but not as high in energy as the staggered conformation that we started with. That eclipsed conformation that we started with. That first eclipsed conformation, that syn conformation there, with the 0-degree dihedral angle between methyl groups is a very tall peak. And the eclipsed conformation we're looking at now, where there is an eclipsed interaction between methyl and proton, that is not quite as unstable. The energy is not quite as high as that first conformation. As we spin that methyl group again, another 60 degrees, we get to the most stable conformation on the graph, which is the anti-conformation. The anti-conformation gives a dihedral angle of 180 degrees between the groups that we're looking at, in this case the methyl groups. And when the largest groups on any molecule, when the two largest groups, the largest on each atom, I should say, when they're 180 degrees apart, that's always going to be the lowest energy conformation. So in this case, those two largest groups being 180 degrees apart, there are no substantial interactions here. We would call this a relative potential energy of 0. We don't have any gauche interactions. There are no eclipsed interactions. So there is nothing in this conformation that's causing any destabilization. As we rotate again 60 degrees clockwise, we get to the 240 degree conformation, where we again have two methyl hydrogen eclipsing interactions and one hydrogen hydrogen eclipsing interaction. That's the same as we saw in the conformation of 120 degrees. So notice how in the graph 120 and 240 have the same energy, and if you compare those two conformations, they have the same interactions, which is two sets of methyl hydrogen interactions and one hydrogen hydrogen interaction. As we rotate again 60 degrees, we get to the 300 degree conformation, and notice that this conformation has the same energy as the 60 degree conformation, the gauche conformation that we saw before. That's because if you notice, we're calling it 300 degrees here, but you could also focus on the other piece of the circle, which is 60 degrees. And that would indicate that those two methyl groups are 60 degrees apart again. So just like they were in that first gauche interaction, the methyl groups were 60 degrees apart. In this conformation that is labeled 300 degrees, those methyl groups are 60 degrees apart again, just on the other side of the molecule. So that 60 degree interaction is going to carry with it the same amount of destabilizing energy. And so the 0.9 kilocals that we saw at 60 degrees is the same 0.9 kilocals that we see at 300 degrees. Those are at the same energy. And finally, as we spin the final 60 degrees, and we are left with that 360 degree conformation that has the same energy as the 0 degree conformation, because again, those two methyl groups are now eclipsing each other. And so that's the highest energy conformation. So a couple of things to point out here. Notice that the syn conformation, where the two largest groups have a 0 degree dihedral angle. In this case, the largest groups are methyls. And those two methyl groups, when they are at 0 degree dihedral angle, that's the highest energy, that's syn conformation. Another point of interest is the anti-conformation, which is when those two largest groups are at 180 degree dihedral angle. That is the most stable conformation. Lowest energy, most stable. And then we have another two staggered conformations that we call gauche. And those gauche conformations are very stable. They are substantially more stable than the eclipsed conformation. You notice those valleys on this graph are pretty close to the lowest valley there at 180, just 0.9 kilocals higher. And so those gauche interactions being staggered are very stable, but not quite as stable as the anti, because that 60 degree separation between those two methyl groups, we're going to see here in the next couple of slides, that does allow the hydrogen atoms to be close enough to each other to interact, which is going to destabilize the molecule somewhat. And finally, we have those other two eclipsed conformations where eclipsed being higher than staggered, it's still a substantial interaction, but because the two methyl groups are no longer eclipsing each other, but they're eclipsing hydrogen atoms, which are much smaller, that interaction is not quite as destabilizing as when the two largest groups, the two methyl groups, are eclipsing each other. So again, remember that the what we're looking at here is drawing a molecule, in this case butane, and we're just kind of rotating that molecule, that one of those carbon atoms, around in a circle. And so you can see in that top set of images there, we're starting at a dihedral angle of 0 along the carbon-2, carbon-3 bond. So you can see that carbon-1 and carbon-4 are methyl groups, and in the conformation that they're drawn here in this representation that we're looking at, the dihedral angle between carbon-1 and carbon-4 is 0 at the top. You can see that the Newman projection that corresponds to that representation on top is drawn right below. And again, you can see there that those two methyl groups have a dihedral angle of 0. They're completely eclipsed. As we rotate now the front carbon, we're rotating that front carbon clockwise relative to the eye. So that eye that's looking at carbon-2, carbon-3, right down that bond, if that was a clock, then carbon-1 is being moved clockwise relative to carbon-4. That's giving us a 60-degree dihedral angle, and we represent the next Newman projection, as you can see down below. So the two-dimensional image, if you will, on top is what you might see in a book or on a test, and what you would have to then draw would be the Newman projection down below that corresponds to that geometry. So finally, in the third image, you can see that again, the back carbon, or carbon-3 in this case, has not changed orientation the whole time. Carbon-2 is spinning along that carbon-2,3 bond, and now we've spun another 60 degrees in that third image, another 60 degrees clockwise. That has given us an eclipsed conformation. You can now see that the hydrogen on top and the methyl on top are now eclipsed. That methyl is eclipsed with the hydrogen in the back, and so on. And finally, if we rotate that front carbon another 60 degrees, then that's going to give us the anti-conformation that we see down below. And so it's important that you start to recognize, as you look at these two-dimensional images of the type that you might see in the top series of images here, that you're able to look at those images. And if I say draw a Newman projection along the carbon-2,3 bond, that you would be able to turn any of those images up above into the Newman projection below, and you would be able to appropriately label it as either eclipsed or gauche or syn or anti, and so on. So remember the nature of this interaction between the methyl groups in the highest energy conformation there, in that syn conformation. We can see here that what's really happening is that those the hydrogen atoms get pretty close to each other. So we talked a bit about torsional strain on Friday when we were looking at the interaction of the bonds in the eclipsed conformation of ethane, and we showed that the electrons within the bonds are repelling each other, and we call that torsional strain. But here in butane, finally we can see that atoms themselves, the valence shell of the atom, the electrons on the very outside of the atom, those electron clouds can bump into each other if the atoms are too close, and we call that steric strain. And so we can see that here in this image, that when we have a totally eclipsed conformation of butane, this is the syn conformation with a dihedral angle of 0, we can see that those hydrogen atoms on those eclipsed methyl groups get pretty close to each other as those carbons, the carbon-carbon single bond rotates around. And so as those hydrogen atoms approach, the energy goes up. And so this is really the nature of that destabilizing interaction when those two methyl groups are eclipsed. The hydrogen atoms just get too close to each other. So we can see here the difference between torsional strain, where we're focusing on the electron pair that's in the bond. So in this case, on the left, the torsional strain, we're looking at a carbon-hydrogen bond. That circle that's unlabeled is a hydrogen. And so in that carbon-hydrogen bond, we can see that there's a pair of electrons. And when those two bonds are eclipsed, in ethane, for example, the eclipsed conformation, those two pairs of electrons are interacting and they're repelling each other. There's a repulsive force because the electrons are negative, so they repel each other. And so that is a destabilizing interaction. And that's the nature of the destabilizing interaction in the eclipsed conformation of ethane. When we look at the eclipsed conformation of butane, we also have that torsional strain because we're still looking at electrons that are within a bonding pair here. They're not shown here. We don't see the dots inside these orbitals, but those dots are still there. So those are still bonds. So we still have torsional strain when we're looking at the eclipsed conformation of butane. But in addition to that torsional strain, we have steric strain because those hydrogen atoms are getting so close to each other. So it's important to note the difference between torsional strain, which is the strain of the bonds, and steric strain, which is the strain of the electron clouds of the atoms themselves as the atoms get too close to each other. And finally, again, this is what gives us these different interactions. When we look at this chart on butane, we can see that we have steric strain and torsional strain when we look at the syn conformation at 0 degrees and 360. That's why that interaction is so high in energy, because we have not only the torsional strain between bonds that we have even in ethane, but we also have this steric strain between those big methyl groups as those hydrogen atoms get too close to each other. That causes that energy to go very high, and so we have a very tall peak. And even in the gauche interaction, when those methyl groups, now they're 60 degrees apart, they are still close enough to have some steric strain. So there is no longer torsional strain. When we look at the 60-degree gauche conformation, there is 0 torsional strain. There's only torsional strain in an eclipsed conformation because that's the only time that the bonding pairs are interacting with each other. In a staggered conformation, the bonding pairs are 60 degrees separate, and so they are not interacting with each other. So in gauche, if we notice that the energy in that gauche conformation is 0.9 kcals above the anti-conformation, what that indicates is that those methyl groups, even when they're 60 degrees apart, they're close enough to each other to interact and destabilize the molecule somewhat. Not much by 0.9 kcals, but more than 0. And so those methyl groups in that gauche conformation, the destabilizing interaction that we see is steric hindrance only. There is no torsional strain in the gauche interaction. And here finally, just to summarize all of these different interactions, we can put the numbers to them. That torsional strain in ethane, where we have two hydrogen atoms eclipsing each other, the hydrogen atoms are too small and too far away from each other to have any significant steric strain. So in that hydrogen-hydrogen eclipsing interaction, it's only torsional strain that we're looking at, and we give that a value of 1 kilocal per mole. So on the right, when we see the all-eclipsed conformation of ethane that has 3 HH eclipsed interactions, then the total relative energy difference between all staggered and all eclipsed is 3 kcal per mole. There are 3 destabilizing interactions, and each of them is worth 1 kcal per mole. The next we can see in propane. In propane, we have a methyl hydrogen interaction, eclipsing interaction. Again, that methyl group and the hydrogen are too far away from each other to be bumping into each other, causing steric hindrance or steric strain. So in this interaction, this hydrogen methyl eclipsing interaction, it's only torsional strain that's occurring here. But because the methyl group is a bit bigger than the hydrogen group, then that torsional strain is a little bit higher. And so the value of that is 1.3 kcals per mole. So when we look at propane, we now have that interaction, methyl and hydrogen, which is worth 1.3, but we also have 2 hydrogen-hydrogen interactions that are each worth 1. So we add those up, 1 plus 1 plus 1.3, and we get a total of 3.3 kilocals per mole difference in energy between the staggered conformation and the all-eclipsed conformation in propane. Finally, we get to butane, and butane has two interactions of interest here. Those are the methyl-methyl eclipsing interaction, the syn interaction between methyl groups, and finally, like we were just saying on the previous slide, we now have torsional strain and steric strain because those methyl groups are so large that the hydrogen atoms can bump into each other, causing steric strain. So the value of that torsional strain and the steric strain combined gives us an energy of 3 kilocals per mole. So, and that 3 kilocals per mole is only the methyl-methyl interaction. So when we're trying to determine the total energy contribution in the syn conformation that we see on the right here of butane, where those methyl groups are eclipsed, we see that the methyl-methyl interaction is worth 3, like we just showed. But there are two other interactions in this molecule, an HH interaction and another HH eclipsing interaction. Those are each worth 1, as we see at the top of this table. So when we add them all up, we have a methyl-methyl worth 3, an HH worth 1, and another HH worth 1. 3 plus 1 plus 1 is 5. So that's why we see that the total value of this energy interaction from the chart we were looking at before is a value of 5 kcals as we add up all of those interactions between the methyl groups and the hydrogens when they eclipse. Finally, we get to this final interaction here, which is notice it's the only staggered conformation on this table. Staggered conformations are generally associated with 0 energy because staggered conformations avoid that torsional strain. And so when we have a staggered conformation, it's a stable conformation and it's usually associated with 0 energy. The only time that we're going to have energy associated, destabilizing energy associated with a staggered conformation is when the two groups that are staggered are within 60 degrees and they're at least as big as methyl groups. So if we have two methyl groups that are 60 degrees apart, we call that a gauche interaction, and that's worth 0.9 kcals per mole. If those groups are ethyl groups, it's also a gauche interaction. They're also large enough to interact with each other, and the energy is going to be even more than 0.9 kcals per mole because an ethyl group is bigger than a methyl group. So the point is, as soon as those groups are methyl or bigger, a gauche interaction, a 60-degree separation between those groups, is not large enough to completely separate them. And so there is a destabilizing energy associated with that. So take a few minutes here to make a Newman projection of 2-methylbutane along the C2-C3 bond. So the first thing you're going to want to do here is draw 2-methylbutane, number the carbons in the longest carbon chain, find carbon 2 and carbon 3, highlight that bond, draw your eye so that you know the perspective that you're trying to draw, and create a Newman projection along that carbon 2, carbon 3 bond. Next, draw a graph of the potential energy versus the dihedral angle for 2-methylbutane along the C2-C3 bond, starting with an eclipsed conformation where the two largest groups are eclipsing each other. That will be 0 degrees on your potential energy graph, and then you will choose a carbon, either front or back, and rotate it in 60-degree increments in a circle until you get all the way around to 360 and you've drawn all 6 different conformations. The 6 conformations that you draw should have 3 staggered and 3 eclipsed conformations. Look at those conformations that you've created, determine if they're the same, the staggered conformations are the same or different, and if the eclipsed conformations are the same or different, and then try to assign energy values based on that table that we just looked at and put energy values on your graph. You will be required to do something similar to this on the next test. Now we'll look at another class of alkanes called cycloalkanes. Most of the same principles that we've already seen apply to cycloalkanes as well as linear alkanes. but there are a couple of differences. So we can see here that the nomenclature is similar. When we have 3 carbons, we call the base propane, prop for 3, ane because it's an alkane. In this case, because the 3 carbons are in a circle, in a cycle, in a ring, we call that cyclopropane. When we have 4 carbons, it would be butane in a line. It's cyclobutane in a ring. Pentane, cyclopentane. Hexane, cyclohexane. Heptane, cycloheptane. So we just add cyclo to the beginning of the prefix when the carbon chain is in a ring instead of in a line. We then use, for example, in the nomenclature of cycloalkanes, we use the cycloalkane as our base. So in the first example, we have a 5-membered ring, so that's pent for 5. It's pentane because it's an alkane, and it's in a ring, so it's cyclopentane. So our base is cyclopentane, and there's a methyl group on one of those carbon atoms, so we call it methyl cyclopentane. Notice how there's no numbering here. We don't call it 1-methyl cyclopentane or 2-methyl cyclopentane. Because the ring is continuous in a circle, there is no beginning or end like there is in a chain, so it's ambiguous where carbon 1 starts. So when there's only one substituent on a ring, if there's only one branch on a ring, we don't have to give it a number. We could call this 1-methyl cyclopentane. If we were to give it any number, we would give it number 1, so it has the lowest number possible. And so we could call this 1-methyl cyclopentane, or we could also call it methyl cyclopentane, and we just assume that that indicates that the branch is at carbon 1. So this is a special case where it's okay to leave the number off. 99% of the time, we number the branches. But in this specific instance, we have a ring, and there's one branch, and it's ambiguous where the first carbon is. It's okay for us to just call it methyl cyclopentane, for example. In the next example, we have a 7-membered ring. So hept, it's an alkane, so it's a heptane, and it's in a ring, so it's a cycloheptane. That substituent there, if we gave it a common name, it would be tert-butyl, but we don't use common names in IUPAC nomenclature, so the IUPAC nomenclature of that branch is 1,1-dimethyl-ethyl, and so the full name of that is 1,1-dimethyl-ethyl cycloheptane. And that's as if we left the first 1 off. So if we had given that branch a number 1, we would call this one 1,1-dimethyl-ethyl cycloheptane, indicating that it was on the first carbon in the ring. But again, it's okay to leave that 1 off in this specific circumstance. Finally, the last example is similar. We have a 6-membered ring. It's an alkane, so we call it a cyclohexane. And this is another branched branch. So the longest chain, the longest branch there has 3 carbons, 1, 2, 3, so we would call it propane. Since it's a branch, it's a propyl. And at carbon 1 and 2 of that propyl branch, we have methyl groups. So we would call this branch 1,2-dimethylpropyl, that's just the branch, and then the base, cyclohexane. When there are 2 or more substituents on a ring, then you number the branches in order to give you the smallest possible numbers. If there are 2 equal ways of numbering the branches so that your numbers would be the same, they would be the same low numbers both ways, then you choose the number, the substituent with the lower alphabetical name will become the substituent with the lower number. So, for example, on this first example here that we see is a 4-membered ring, which 4 is butane, and if it's a ring, it's a cyclobutane. And so we have 2 substituents. We could number these substituents 1, 2 from the bottom to the top, as is shown, or we can number them 1, 2 from the top to the bottom. Numbering both ways gives us the same numbers. So when we come to a situation like that and we have to break a tie, the way that we break the tie is by giving the lower number to the substituent whose letter comes first in the alphabet. So for example, in this case, we have an ethyl and a methyl. So because ethyl has the lower alphabetical, the first letter in the alphabet, E versus M, then we would give that substituent the lower number. The next example is a 5-membered ring, a cyclopentane. And it has 3 branches, 2 methyl groups at carbon 1 and 1 methyl group at carbon 3. So we could we would get a 1 and a 3 regardless of which way we started the numbering. The reason that we give the 1 to the 2 methyls is because, remember, we have to number every branch, even if that gives us the same number twice or more than twice. So if we have 2 branches on carbon 1, then it would be a 1, 1, 3 as shown. But if we had reversed the numbering and we had given the 1 to the single methyl and the 3 to the double methyl, then our numbers would be 1, 3, 3. And 1, 1, 3 has lower numbers than 1, 3, 3. So we give the 1 to the group that has the carbon that has 2 methyl groups. Finally, in the last example, we see that we have a 6-membered ring, a cyclohexane, and in this case we have 3 branches again, 2 branches at what is going to be carbon 1 and 1 branch at carbon 4. So in this case, the book will sometimes use this isopropyl nomenclature interchangeably. And so remember, we would call this branch, rather than isopropyl, we would call this 1-methyl ethyl. And still, it wouldn't change the numbering because the ethyl group here is still going to have a lower number because there are 2 of them. So that would give we would have 2 1s and 1 4 in this example because of the position of the branches. So we would call this one 1,1 diethyl because of those 2 ethyl groups on carbon 1, 4 1-methyl ethyl in parentheses cyclohexane. The final thing that we have to be aware of when we're looking at the nomenclature of cycloalkanes and how it differs from linear alkanes is that in linear alkanes, we've looked at a situation like this. Remember, in class I showed 2 chlorines on the same side of the molecule, and then the bond rotates and the 2 chlorines are on opposite sides of the molecule. And we said that that was the same molecule when we're looking at a linear alkane, because there's nothing stopping that bond from rotating all the way in a circle. And so those 2 chlorines can change positions as that bond rotates. But if we look at a ring is prevented from rotating because the bond goes all the way around in a circle. If you imagine trying to make a model of this ring, these single bonds cannot rotate anymore because they are stuck to the atoms next to them, which are stuck to the atoms next to them, and so on around in a ring. So there is some amount of motion that can happen in a ring, but it can't spin all the way around in a circle like a single bond can in a chain. So single bonds in rings have less mobility than single bonds in chains do. And we can see that effect here. Remember, in a double bond, an alkene, alkenes cannot rotate freely. Single bonds can rotate freely, but double bonds can't. So when we look at the similar situation in an alkene that we have here, we call them cis and trans isomers. They are not interchangeable because there's no free rotation around that bond, and these are 2 different molecules. Well, something similar happens in cycloalkanes because of this restricted rotation, because the atoms are stuck in a ring. That restricted rotation causes these groups to not be interchangeable anymore. We can't rotate these bonds around in a circle to give us the structure on the left and turn it into the structure on the right. So then we have to give them separate names to distinguish these two separate stereoisomers, just like we do above, cis and trans butene. We would call these cis and trans 1,2-dimethylcyclopentane. So let's break that down for a minute. When we look at that molecule on the bottom, we see that it's a pentane. It has 5 members in a ring. It's a pentagon. And so they're all single bonds. So it's a pentane, a cyclopentane. And there are 2 branches, a methyl group on one carbon and a methyl group on the carbon right next to it. If we look at the difference between that structure on the left and the structure on the right, we can see that the structure on the left, both methyl groups have dashes. The structure on the right, one methyl group has a dash and one methyl group has a wedge. So if we were trying to name these without cis and trans, I would call the one on the left, I would call it 1,2-dimethylcyclopentane. And the one on the right, I would call it 1,2-dimethylcyclopentane. So they would have exactly the same name because those branches are in exactly the same place. There's one on carbon 1 and there's one on carbon 2. So they're exactly the same. So this is what's meant by stereoisomer. The branches have the same numbers. So how do we distinguish these two molecules from each other? Well, we can say the same thing about the alkenes above. There's a methyl on carbon 1 and there's a methyl on carbon 2. In this case, we're looking at a butene chain, but if we were to call the carbons in the double bond, carbon 1 on the left and carbon 2 on the right for the carbons in the double bond, then each of them has a methyl group on it. So in that way, the methyl groups are connected to the same atoms. There's the same connectivity, the same connections, but the groups have different positions in space. On the one on the left, they both point down. The one on the right, one points up and one points down. So these are called stereoisomers. And so because we would end up giving them the same exact name, 1,2-dimethylcyclopentane, but they're not the same exact molecule, these are 2 different molecules, then we have to come up with some way to name them differently. And so them being stereoisomers and those methyl groups having different positions in space, we call the one on the left cis. They're both on the same side of the ring. And we call the one on the right trans. They're both on opposite sides of the ring. So to summarize the nomenclature of cycloalkanes, if there's only one substituent on the ring, you don't need to number it. For example, 1-methylcyclohexane is equivalent to methylcyclohexane. If there are 2 or more substituents on the ring carbons are numbered to give the lowest possible numbers for the substituted carbons. The numbering begins with one of the substituted ring carbons and continues in the direction that gives the lowest possible numbers to the other substituents. When the numbering could begin with either of 2 substituted ring carbons, as in a disubstituted cycloalkane, begin with the one that has more substituents. Otherwise, begin with the one that is first alphabetically. When there are 2 stereoisomers possible with respect to the position of the substituents on a disubstituted cycloalkane, then the cis or trans prefix must be added to distinguish between them. So this chart shows us the ring strain as a function of ring size. And we're not going to look too much at this chart at this point, except I want to draw your attention to 2 parts of the table. So first, look at the ring size, 3, 4, 5, 6, 7, 8. And entry 6, if you follow that all the way to the right, you see that there is 0 kilojoules of ring strain for cyclohexane for a ring size of 6. And also, the very bottom of this table says the reference a long chain alkane has a total ring strain that is also equal to 0. So all the other entries on here, ring size of 3, 4, 5, 7, 8, they all have some ring strain associated with them, but cyclohexane does not, 0 kilojoules. and neither does a long chain alkane, 0 kilojoules. So we'll start with cyclopropane, which is the simplest cycloalkane. It has 3 carbons in a triangle. When you connect 3 of any point, you get a triangle of some sort. Because these 3 carbons are equivalent, you get a symmetric triangle, and we call that an equilateral triangle. And so all of the angles are equal at 60 degrees. All of the bond lengths are equal. And when we look at the carbon atoms in any cycloalkane, there's only single bonds, and every carbon atom has 4 bonds. And so every carbon atom is sp3 hybridized in a cycloalkane. And so we know that sp3 hybridized atoms adopt a tetrahedral geometry, and that gives them 109.5 degree bond angles. So all of these sp3 hybridized atoms would have an 109.5 degree bond angle if it weren't for them being stuck in this triangle shape. So this triangle shape prevents them from having a 109.5 degree bond angle, because in a triangle the angles must be 60 degrees. So the difference between 109.5 and 60, we call that angle compression or ring strain. So the ideal angle for these atoms would be 109.5, but it's squeezed down to 60, so there's 49.5 degrees of angle compression or ring strain in cyclopropane. Notice also that these bonds are not very strong because the overlap of these orbitals is not very great. The orbitals are not pointing at each other very well. We would call them bent bonds maybe, and so they're very weak bonds. If we look at a Newman projection of cyclopropane, we see that all of the atoms are eclipsed. So no matter which bond we look down, what we will see is 2 sets of eclipsed hydrogen atoms. And so all of the atoms in cyclopropane always adopt this eclipsed conformation, because when you only have 3 points, there's no way that you can prevent this all eclipsed conformation. Those 3 points must lie in the same plane. If we look at cyclobutane, we see that it has some angle compression as well, because cyclobutane is a square. Squares have 90 degree bond angles, and so if we have 4 carbon atoms that are all equivalent, they're going to form this square shape. And although they're sp3 hybridized, and so we would expect their bonds to be 109.5 degrees, in a square they're constrained to 90 degrees. So we have this 19.5 degree angle compression, or 19.5 degrees of ring strain, that's inherent when we have cyclobutane, when we have this square shape. So notice also, if we look at the Newman projection, we also have these eclipsed conformation. And remember that eclipsed conformations come with torsional strain. So cyclopropane, with the 3-membered ring, the triangle, has ring strain and torsional strain because of those eclipsed conformations. And cyclobutane here has ring strain and also torsional strain because of these eclipsed conformations, because of those bonds. The electrons in the bonds have a repulsive force. So cyclobutane can do something that cyclopropane cannot do, though, and that is that it can bend out of plane. So if we have those 4 atoms and they're all flat, and we put all 4 atoms, for example, on a table and squish them down so that they're flat, then all of those, all the conformations are going to be eclipsed, just like we saw in cyclopropane. But if we kind of bend the shape, slightly fold it or pucker it, take one of those atoms and kind of push it up or push it down relative to the other 3 atoms, as you can see in these shapes on the screen. If we do that, then what we do is we kind of bend the bonds just enough so that those atoms are not quite eclipsed anymore. So notice that when we do that, we go from 90 degrees, and when we pucker it and we bend it out of plane, we decrease the bond angle. It goes from 90 degrees down to 88 degrees. It gets smaller. So what that means is that we're increasing the ring strain. But we're at the same time, as we bend it out of shape like that, we're also relieving the torsional strain because we're also preventing those eclipsed conformations. If we look at the Newman projection, those H atoms are not quite eclipsed anymore. They're not quite in front of each other because we bent those bonds a little bit. So although we're adding ring strain and we're making the molecule slightly more unstable because of that, we're also relieving torsional strain. And in fact, we're relieving more torsional strain than we are adding ring strain. So this is overall a benefit to the stability of the molecule. Making this change, bending it out of shape like this, makes the molecule more stable. So now let's look at cyclopentane. If we look at a pentagon, just a regular symmetric pentagon that's flat, that's two-dimensional, the bond angles of the pentagon are 109.5 or 110 degrees. So the bond angles of a pentagon are actually just right for the bond angles of an sp3 hybridized carbon. So if all of the atoms in cyclopentane were flat, and we've pushed them all down flat on a table, and they were all in the same plane, they would have zero ring strain, zero angle strain in cyclopentane. However, all of those hydrogen atoms would be eclipsed. When all of the atoms are flat, then all of the Newman projections would show a completely eclipsed conformation for all of the hydrogen atoms. There's no way to avoid it when they're all flat, lying in a plane. So just like we saw with cyclobutane, in cyclopentane, the atom kind of deforms a little bit, the molecule deforms a little bit, and it becomes not planar, not flat. It bends itself out of the plane, as shown here, to prevent that all eclipsed conformation. So now you can see here that the Newman projection shows those hydrogens are not eclipsed, but only because the pentagon is not flat. It's kind of skewed. It's bent out of plane. So we do this at the expense of ring strain. Remember that if the pentagon is flat, it has zero ring strain. But if we bend it like this and we bend it out of the plane, we're squeezing those angles and we're kind of constraining them a little bit. So the angles are actually a little bit less than 109.5 in this skewed conformation of cyclopentane. But just like in cyclobutane, we add ring strain. It's true, when it bends out of shape and it puckers like this, we're adding even more ring strain, but we're relieving so much torsional strain because of those eclipsed conformations, avoiding those eclipsed conformations, that overall it's worth it to the molecule, and it becomes more stable because of that. Now, the cyclobutane conformation has a special name called the puckered conformation, and the cyclopentane also has a special name called the envelope conformation. And that's kind of because if you squint at this picture on the left and you look at this where the green arrow is pointing, that's the part of the envelope that you lick, and then after you lick it, you fold it over and you would make the letter. So you can kind of see it kind of looks like an envelope. If you were to connect those two corners, that would make the top of the letter. And so that's why they call this the envelope conformation. That it's kind of the flap that points upward there. Okay, now finally we get to cyclohexane. And remember, cyclohexane was special when we looked at our chart. A six-membered ring has zero ring strain. And so if we think about a triangle, it has 60-degree angles. A square has 90-degree angles. A pentagon has 110-degree angles. A hexagon has 120-degree angles. So a hexagon has, the angles are too big. And so the sp3 hybridized carbon is 109.5 degrees, but the angles of a hexagon are 120 degrees. So you would think that cyclohexane would have angle strain in the opposite direction because it would be trying to make the angles too big instead of too small in this case. However, remember that those angles, when we're thinking about the angles of a pentagon or a hexagon in this case, we're thinking about angles when they're flat on the ground, when all of the points are in the same plane and it's flat. However, remember when we bend the shape out of plane, then we're actually squeezing those angles down so that they're a little bit smaller than they'd otherwise be. So it turns out that cyclohexane can actually bend out of plane quite a bit. So instead of having 120-degree angles, when it bends out of plane in the specific shape that we see on the screen here called the chair conformation, the angles actually become 109.5 degrees. So it actually has perfect tetrahedral angles when it bends itself in this specific shape. And also, when it bends itself in this specific shape here, if you look at the Newman projection, it has a perfectly staggered conformation. So all of the H's are perfectly 60 degrees away from each other in an all staggered conformation, as far away from each other as they can be, so that this group here, when cyclohexane is in this specific shape called the chair conformation, it has zero angle strain and also zero torsional strain. It's a zero strain shape. And they call it a chair because you can kind of see that guy on the bottom there is kind of in one of those lounge chairs like you might see by the pool. And so it kind of has that shape where part of it goes up and then you've got the flat part where you sit, and then part of it goes down where you put your feet. That's kind of why they call it the chair conformation. So another thing to notice about this slide here is the Newman projection. So notice how this Newman projection seems like it has two Newman projections stuck together. But it is two Newman projections stuck together because this is a Newman projection that represents the entire molecule cyclohexane. So cyclohexane has 6 carbon atoms. So if we look at this Newman projection down below, we can track where all 6 are. Let's start with the CH2 that's down below, and then we will go clockwise around in a circle and track all the carbons. So starting with the CH2 that's at the very bottom, at 6 o'clock, if you will. That's 1. And then if we go to the CH2 that's going to be to the left of that, clockwise, is going to be the point at the dot right in the middle of the first Newman projection. That's carbon 2. And then the circle right behind that, that would be carbon 3. And then the CH2 at the top, that would be carbon 4. And then the circle at the back of the next Newman projection would be carbon 5. And then the point at the front of the second Newman projection would be carbon 6. And then we get back down to the CH2 at the beginning. So we have 2 carbons in each Newman projection and 2 carbons in the middle, on the top and the bottom. So that's 2, 4, 6. 6 carbons altogether. So notice how the perspective, looking from the top, you can see those eyes looking down at the chair. So when we look down at the chair, you can see that there is the headrest where the man's head is sitting. That's kind of at the very top from your perspective where your eyes are sitting. That's the CH2 that's at the very top of this Newman projection. It's kind of like you're looking at the chair with the footrest and the headrest kind of superimposed in front of each other. So then the CH2 that's at the very bottom of that Newman projection, the bottom one, that's the footrest that you see at the very bottom. And then the lines that you're looking down, those are the 2 lines here that would make the flat part where you would sit on the chair. And that's how you would interpret this Newman projection. So finally, back to this chart, we can see that cyclopropane has a lot of ring strain, 38.5 kilojoules per CH2 group, or a total of 115 kilojoules for all 3. And so you don't need to know any of these numbers. The point is to just look at the magnitude of the ring strain as a function of that angle compression. So in cyclopropane, a ring of 3, we have about 50 degrees of ring strain from 110 down to 60. And in a ring of 4, we have bond angles of 90 degrees. So we have about 20 degrees of ring strain there, which equates to 27.5 kilojoules per CH2 group. When we have a ring size of 5, remember that cyclopentane, the pentagon, has ideal bond angles when it's flat, but when it bends out of plane, those bond angles get squeezed a little bit tight, so it has a very small amount of ring strain at 5.4 kilojoules per CH2. Cyclohexane has 0. And then when we get bigger than cyclohexane, those angles start to become too big, right? Just as we had suspected might happen with cyclohexane but didn't because it got squeezed down, that does start to happen with cycloheptane and cyclooctane and so on. Those angles start to become too large, and we start to have angle strain in the opposite direction, where the ideal angle, 109.5, is too small for the geometry restraint of those larger polygons. So chairs do not have many conformations. When we look at the conformation diagram of butane, we had 2 different staggered conformations and 2 different eclipsed conformations, and it was kind of a complicated graph that we were looking at. Now, this graph does show that there's a lot of different conformations involved in what we call the cyclohexane chair flip. This graph is analogous to what we were looking at with ethane and propane and butane, where we spin a carbon around in a circle, around a bond that can rotate, and we look at the energy, how the energy of the molecule changes as those groups get close to each other, as we spin around those single bonds. So that's what's happening here too, except remember, in a ring, we can't really spin in a circle because there is some constraint because those atoms are all stuck to each other. So in a ring, we can't go all the way in a circle, but we can the atoms kind of jostle around and switch positions. So in cyclohexane, they can go from one conformation, one chair conformation, where the headrest is carbon 4 and the footrest is carbon 1. We see that on the left. And then the headrest and the footrest switch positions. So then look at the position on the conformation on the right. Now carbon 4, it was the headrest on the left, and now it's the footrest on the right. Carbon 1 was the footrest on the left, and now it's the headrest on the right. So the footrest and the headrest change positions, essentially, is what happens in a chair flip. They can't go all the way around in a circle. We don't have to go in 60-degree increments like we do with the linear alkanes. That's not possible with a cycloalkane. There's really only 2 conformations that we really have to be worried about. These chair conformations, the one on the left and the one on the right. They look very similar, and they are very similar, but notice that positions 4 and position 1, for example, have been inverted. And so have the other positions, 2, 3, and 5, 6, and we'll see that in a moment. So on the way from one chair to another, we go through these positions, the half chair and the boat and the twist and so on. And so there are other conformations that occur in cyclohexane, but they're not stable. Notice how all of those other conformations, including the twist, which is the lowest energy up there, even the twist is a high energy conformation compared to the chair. So it's true that there are other conformations available to a cyclohexane molecule, but they're such high energy relative to the chair that they only happen on their way from one chair to another. They only happen during the chair flip. So we don't focus on them. We're not going to focus on the half chair or the boat or the twist. They exist, and we go through those different conformations on our way from one chair to another, but because they're not very stable, we're only going to focus on the 2 chair conformations on the left and the right. All right, so this is kind of a ball and stick version of cyclohexane. And what we're going to highlight here are the 2 relative positions of atoms that are stuck on the 6 different atoms in cyclohexane. So from here on out, we're really going to focus mostly on cyclohexane because, as we saw before with the ring strain, cyclohexane is particularly stable. It has access to these 2 conformations, and so that makes it fairly abundant. And we see a lot of 6-membered rings in biology, for example. And so we're going to focus a lot on cyclohexane here for a bit. When you look at the pink atoms on the left, the pink H's, they're all kind of pointing straight up and down, and you see they have the parallel pink lines. The bond is either pointing up, like 3, 5, and 1, or the pink line is pointing down, like in 2, 4, and 6. Those pink atoms have a relative position that we call axial. The axial position is one, as you can see in the image to the right now, you can see that the axial atoms, the red atoms, kind of sit on the top and the bottom of the ring. Axis, as if the cyclohexane were a globe, and those are the North Pole and the South Pole is where the axial hydrogens are, or the axial groups. If we now look at the green groups, those green ones around the side, they're all kind of like pointing up or down a little bit, but they're all mostly kind of pointing to the side and away from the ring. We can see that in both representations on the left and the right there. So those are called equatorial groups, and that's because, again, if we picture this cyclohexane as a globe, then the green would be the equator. And so all the groups that kind of go around in a circle in the equator are the equatorial groups, and all the groups that are at the top and the bottom are the axial groups, like the axis. So what you can see in those groups, the images on the very bottom, are again that the axial groups really sit on the top and the bottom of the ring, and that those equatorial groups kind of sit out on the sides of the ring. And the sides of the ring are different than the top and the bottom because the sides of the ring have more space than the top and the bottom of the ring. So groups that are on the equatorial position are generally more stable than groups that are in the axial position, because if you're in one of these green positions, there's more space for you to spread out, and if you're in one of these red positions, you're more likely to bump into atoms that are also in a red position. The red positions are closer to each other. The green positions are further away from each other.
Chemistry. Next, we'll look at drawing chair conformations. Your books are using computer-generated graphics, so they're perfect. But when you try to imitate it, you wind up getting something that looks like this, where it looks a little bit like a duck and not very much like a chair. Instead, let's go with a very simple method that will give you a foolproof chair every time. Draw two parallel lines that are slightly offset from each other. In this case, I have the left over the right, or you could have done the same thing, right over left. Then, we're going to place two dots towards the opening, but like before, the dot over the upper opening is going to go slightly above. The dot below the lower opening will be slightly below. And then once again, we connect the dots. As you can see, it looks nothing like the bow tie structure, and it doesn't look very much like the chairs in your book, but it's very obvious looking at this structure what is going on. I see which is the carbon facing up, which is the carbon facing down, and I can tell exactly where the other carbons are located. But it doesn't stop there. Once you have a cyclohexane, you need to add in your substituents. I like to start with the substituents at the tips, where the tip gives us the direction. The up tip, as I call this carbon, will have an axial substituent straight up. The down tip will have an axial substituent straight down. You can start with either the up tip or the down tip. Only one of them is needed, because then you're going to follow the pattern of up, down for the axial substituents. Now, if you're uncomfortable with the concept of chair conformations, axial and equatorial, pause this video and go watch my chair conformations tutorial link below, or visit my website, leiaforsyth.com/chairs, to learn about what goes into the chair conformation. If you're already familiar with that, let's continue. We'll start with the up tip and then alternate the pattern. Up, already have the down, up, and down. These are my axial substituents, and identifying the tip of the chair made everything else fall into place regardless of drawing skills. Next, we'll add our equatorial substituents, remembering that each carbon has one axial and one equatorial, and that they're facing in opposite directions. So if the axial substituent is facing up, the equatorial substituent has to be facing down, and this allows me to start the same pattern of up, down, starting with any one carbon where we identify the direction of the axial substituent, put the equatorial substituent in the opposite direction, and continue the pattern. Before we do so, let me point something out. I've seen a lot of students lose points by doing this. It appears to be up and down. The problem is, if you draw a parallel line, I can't tell if that pink equatorial substituent is facing up or down. And if your professor can't tell, you're likely to lose points. So make sure that it's very obvious for each equatorial position whether it's facing up or down. And the way you can verify is to draw a parallel line and make sure your substituent is well above or well below. We determined that this is a down equatorial, making this up equatorial, down equatorial, up equatorial, down equatorial, up equatorial. Those are all my substituents. One more thing to point out is the two middle carbons tend to get confusing. If we think about what we're looking at here, this is a cyclohexane. This is a ring that we're looking at straight on. That means this substituent here isn't really facing to the right or left, it's coming directly at you. But if we show it just as a dot, implying a substituent coming out, it's hard to tell what's going on. So instead we offset it slightly to the right or slightly to the left. It doesn't matter so long as we kind of see what's going on and recognize that's an equatorial substituent facing down below the plane of the cyclohexane. Now that you have the basic chair conformation, we want to add substituents, and we want to make sure they show up in the right place. Anytime you're asked to turn a cyclohexane into a chair conformation, don't think about the substituents right away, because trying to take this molecule and force it into a chair conformation is time-consuming, confusing, and often gets messed up. Instead, here's what I want you to do. I want you to start your drawing by completely ignoring the molecule that you're drawing. In this case, we're not told which substituent should be up or down, so we're going to draw just one version of the chair. To do this, we'll start by drawing one random chair. So we have the parallel lines, we have the dot, connect the dots. Once you get comfortable, you can just imagine that dot and connect to an imaginary dot. We have the skeleton. Next, we'll add the substituents. I'll start with the up tip. This is something that I call the turning your brain off part. You're going to spend a lot of time in orgo thinking, but certain aspects are much easier if you just turn off the brain, go with the flow, and prepare for the next step. So find your up tip and just turn off the brain. Go up, down, up, down, up, down. Don't really think about what else is going on here. And then do the same thing for the equatorial substituent. We identify that this is axial up, so we'll start with equatorial down, up, down, up, down, and up. We have a skeleton, now we're ready to turn it into a chair. In order to add the substituents, we want to make sure that we know which substituents go where by relating the two molecules. And to do this, we'll number the carbon chain. It doesn't matter how you number it. This would be incorrect if I'm naming it to make the methyl number 1, but I'm not naming it. I just need a reference, something that I can follow to convert one to the other. I decided to number this counterclockwise randomly, just because. So we'll have to do the same thing and number this one counterclockwise. It doesn't matter where I start because it's a ring. So I will randomly put the number 1 here and continue counterclockwise 2, 3, 4, 5, and 6. Now that I know which carbon on the chair corresponds to the carbon on the flat drawing, all I have to do is identify a substituent, ask whether it's up or down, and place it on the same carbon. Carbon number 1 has a methyl group on a wedge, which is up, and so carbon number 1 gets a methyl group up. Up happens to be equatorial, but I didn't know that before drawing the chair, and it didn't matter. All I had to recognize was carbon 1 has a methyl on a wedge. The wedge is up. Find carbon number 1, find the position that is up and add the methyl. The position that is up happened to be equatorial, and so I know the methyl group is equatorial. The numbers tell us what's going to happen. Next, we have an OH group up on a wedge on carbon number 3. So we find carbon number 3, identify the up position, and hey, that happens to be equatorial. Great. Put an OH group in the up position. And lastly, on carbon number 5, we have a bromine on dashes, meaning it's going down into the page. So we identify carbon number 5, put the bromine on the down position. In this case, down happens to be axial, and so we have our final substituent. If this is your quiz or exam and the lines are all present, do make sure to add in the hydrogens. Otherwise, you may lose points because that line without a hydrogen actually means a methyl group. So we'll throw those in there. And that's it. There you have your chair conformation. What happens if you're asked to draw the ring flip for the chair conformation? Once again, we don't really want to look at the chair that we have. Instead, we want to use a simple approach to flip that chair and then do the same thing that we did here by adding the substituents back. The first step in drawing a ring flip is identifying the pattern. Remember, to draw a chair, we had two parallel lines slightly offset from each other. And in this chair, the left is above the right. To do the ring flip, we're going to need the opposite chair, so we're going to draw the two parallel lines where the right is above the left. Then we're going to add a dot or have an imaginary dot that we can connect the lines. Same thing here. Notice it's not very neat, might not pass an art class, but it's very obvious for organic chemistry. Next, we're going to do the same thing with the substituents. I like to start with the up tip. So we have up, down, up, down, up, down. Those are axial. Next, we have equatorial, down, up, down, up, down, up. Then we want to number, and this is where you want to be careful. You should definitely practice this with a model kit just to make sure you understand how the ring flip occurs. I show you how to do this with a model kit in the video link below. We can easily do the ring flip on paper by identifying the up tip or down tip carbon and flipping it to the opposite direction. If we grab the up tip, carbon number 2, and drag it down, that gives us carbon number 2 down on the bottom right. We could have done the same thing to carbon number 5, the down tip, and drag it up, which gives us carbon number 5 here. Now the most important part is your direction. If my starting molecule has the numbers counterclockwise, make sure your ring flip is also counterclockwise. Otherwise, you potentially create the enantiomer, which is not what we're looking for. To number this counterclockwise, we have 2, so let's continue 3, 4, 5, 6, and 1. And here's the best part. We're not figuring out where the substituents are. We're simply letting the numbers direct us. On carbon number 1, I have a methyl group in the up position. I don't care where or what is going on with that up position. I simply care about putting a CH3 up position on carbon number 1. Same thing for carbon number 3. OH in the up position. Identify carbon 3. Add an OH in the up position. And carbon 5 has Br in the down position. So we identify carbon 5, find the down position, and add a bromine. Make sure to add in the hydrogens. And that is it. The key thing that I want you to take away from here is that we're not looking at this molecule and trying to recreate it. Instead, we're looking at the pattern within the molecule, identifying where the numbers are, the direction, and using the numbers to determine where I add the substituent rather than trying to visually rotate something in your head that is honestly just going to be confusing. How do you feel about drawing chair conformations? Are you ready to do some practice problems? First, make sure to give this video a thumbs up, then click the subscribe button and bell icon so that you don't miss any of the new videos. Then go try the chair conformation practice quiz, which you can find on my website along with the entire chairs tutorial series, leahforsyth.com/chairs. Leah here.
So as you saw in the video, drawing a chair flip is an important component of this section. On the test, you're going to be asked to identify what's happening in certain chair flips, but you're also going to be asked to draw the most stable conformation of a certain molecule. And generally, the only way to do that is by drawing both conformations, both chair conformations, and determining which one is the most stable by determining which one has the biggest substituents in the equatorial position. So make sure that you practice drawing these chairs and that you practice drawing chair flips. It's going to be important that, as you saw in the video, that I can interpret whether your positions are axial or equatorial and whether they're pointing up or down. And that's not arbitrary because it's difficult to draw these the right way. So the video has a very straightforward way to draw them reproducibly every time. So I would definitely recommend practicing your drawing and practicing with the method that was introduced in the video. So notice again how if we think about the chair as a lawn chair, then we can see here in the image on the left, carbon 1 is the headrest and carbon 4 is the footrest. And then after a chair flip, let's skip the boat and we'll go all the way to the image on the right. What was the headrest, carbon 1, is now the footrest. And what was the footrest, carbon 4, is now the headrest. So essentially, the headrest and the footrest change positions in a chair flip. That's the easiest way to think about it. And when that happens, the other carbons, 2, 3, and 5, 6, also are changing positions. They're going from up to down, if you will. But when we draw 1 and 4 as though they have switched positions, the others just fall in place. So it's really conceptually the easiest to think about. That's what you're trying to do, is to exchange the position of the headrest and the footrest. And so also notice here that when we have an axial group, the image on the left, we have a methyl group in the axial position. And in the image on the right, we have a methyl group in an equatorial position. So what I'd like you to notice here is that methyl group, when it's in an axial position, that purple proton is very close to those red protons that are also axial. Those axial protons are on carbons 3 and 5 in the ring, and they're pointing up, straight up. They're in the axial position. And there's a bit of steric hindrance there between the hydrogen atom, the purple one on the methyl group, and the red ones that are in the axial position on the ring. They are close enough right there to bump into each other and cause some steric repulsion. If we look at the image on the right with the equatorial methyl group, you will see that the protons, the purple ones, are no longer really bumping into any of the groups. They don't really bump into those red protons. They're not really bumping into the green protons. Everything seems to have enough space when that methyl group is in an equatorial position, when it's off on the side of the ring like that. So this is what I had kind of mentioned earlier, was that the equatorial position, those groups are further away from each other, and they're further away from the groups in the ring when they're in the equatorial position. So that gives them more space to spread out. So that makes them more stable. So when large groups are in the equatorial position, they're more stable than when they're in the axial position. And when they're in the axial position, they're too close to the axial groups in the ring, and there is increased steric hindrance. So notice how in carbon 1, the headrest, we have the axial methyl group, and then after the chair flip, that axial group becomes equatorial on carbon 1. The headrest becomes the footrest, and the axial group becomes equatorial. So during a ring flip, every axial group becomes equatorial, and every equatorial group becomes axial. That's what's happening during a chair flip. The axial groups and the equatorial groups are changing places. But what's not happening during a chair flip is up and down are not changing places. So look at carbon 1 on the left. The methyl group is axial and it's pointing up. Look at carbon 1 on the right. The methyl group is equatorial, but it's still pointing up. So Axial becomes equatorial during a chair flip. Equatorial becomes axial. They change positions, but up stays up and down stays down. That that methyl group at carbon 1 is pointing up in the left and on the right. The H, the equatorial H at carbon 1 is pointing down on the left and on the right. They're switching between equatorial and axial during the chair flip, but they are not switching between up and down. Up stays up and down stays down. So when we think about the nature of this steric interaction, we can look at what's happening if we focus on a Newman projection. So when I have a methyl group in an axial position, like we saw in the previous slide, it's pointing up relative to the ring. So that's that carbon 1 right there. We have an axial methyl group. It's pointing up relative to the ring. And if we draw a Newman projection down bonds carbon 1 and 2 and 5 and 4, as indicated on the left there, what we see is that that methyl group, when it's pointing up, it's 60 degrees away from another, essentially a methyl group, right? That CH2 is not a methyl, because a methyl is CH3, but CH2 is pretty similar to CH3, probably similar in size, and has 2 hydrogens, if not 3, and so it still can likely cause some steric hindrance, and in fact, that's what's happening. That carbon methyl group that's pointing up at carbon 1 is gauche to carbon 3 that's in the ring. So there's a 60-degree separation between that axial methyl group and the carbon that's actually inside the ring. And it doesn't matter whether we look at it from the left side or the right side, as it were, as we can see that these two Newman projections are just showing us that when we look at the interaction from the right, as we see on top, there's a gauche interaction between carbon 1 and carbon, or the methyl group on carbon 1 and carbon 3 that's in the ring. And if we look at the Newman projection on the bottom, we can see that that methyl group on carbon 1 is also interacting with carbon 5. It's also gauche to carbon 5. So there's actually 2 gauche interactions here between the methyl group that's in an axial position and the carbons that are within the ring. So we call this a 1,3 diaxial interaction, and this is because that carbon is actually the axial methyl group is actually interacting with 2 of the carbons in the ring and causing steric hindrance. So in addition to us just being able to look at that structure and saying, yeah, when the methyl group sits on top, it seems to be getting closer to those hydrogens, we can actually look at this in the Newman projection too and see that we already have a term for how close those carbons are getting, and we call it gauche. And so that carbon, that methyl group, is gauche to 2 other carbons. When a methyl group is in the equatorial position, it avoids that gauche interaction. So look at the difference here. See that H that has a 2 underneath it, that's where the methyl group was. And when the methyl group was up there, we called it axial because it was pointing straight up and down. And when it's axial, it's 60 degrees away from carbon 3. But when it's equatorial and it's pointed in the position that it's at now, it's actually anti to carbon 3. And in fact, it's also anti to carbon 5 on the other side. So not only is it anti to the first carbon, as we saw previously, but it's anti to both. So when the methyl group is axial, it's gauche to carbon 3 and 5, and when the methyl group is equatorial, it's anti to carbon 3 and 5. So this interaction, this 1,3 diaxial interaction, when I have a methyl group that's axial and it can interact with the carbons in the ring, that is a destabilizing interaction. And in fact, when the methyl group is equatorial, it's more stable than axial by about 1.7 kilocalories per mole. So just as we had seen previously when we were looking at ethane and propane and butane, we were able to quantify the relative stability of these interactions, the difference between a syn interaction and a gauche interaction and a hydrogen-hydrogen eclipsing interaction. We can do the same thing, or an analogous thing here, with the positions of the groups on a ring. And so just as before when we were looking at the conformations of butane, and we could say the anti-conformation is the most stable conformation of butane, we're going to make similar comparisons now with cyclohexane, and we're going to look at these two conformations and we're going to determine which one is the most stable based on these numbers, based on determining which conformation gives the largest groups in the most equatorial position, because equatorial is a more stable position than axial, because equatorial avoids this 1,3 diaxial interaction. So this table shows some of the energy differences between the axial and equatorial conformations of monosubstituted cyclohexanes. So X is just going to be whatever group we see in that first column, and the difference is just going to be whether that group is equatorial or axial, and the amount of energy that is the relative stabilizing or destabilizing energy, depending on how you want to look at it, of that group. So for a fluorine, for example, it doesn't matter much whether a fluorine is equatorial or axial. That's a fairly small number there, 0.2 kilocalories per mole. If we look at whether an OH is equatorial or axial, that's 1 kilocal per mole. So that's equivalent to a hydrogen-hydrogen eclipsing interaction. If we look at whether a carboxylic acid group is equatorial or axial, that's equal to 1.4 kcals per mole. So that's about equivalent to a methyl hydrogen eclipsing interaction. A methyl group by itself is equal to 1.8 kcals per mole when it's equatorial versus axial. So that methyl group is actually fairly destabilizing when it's in the axial group, more so than all of these groups that came before it, which is kind of surprising. An ethyl group and a methyl group are nearly the same, 1.8, 1.9. When we get an isopropyl group, it's a little bit bigger than an ethyl. That brings it the kcal per mole to 2.1. And finally, that final group on the bottom there is a tert-butyl. Notice that the tert-butyl, the difference between an axial and an equatorial tert-butyl, is 5.4 kcals per mole, which is more than twice the amount of the previous group, which was an isopropyl. And a tert-butyl is not more than twice as big as an isopropyl. So it's kind of a surprising finding that a tert-butyl would have a number that's so much higher than the isopropyl. And so we'll see why that is here in a minute, but it's important to recognize that if we can say that the methyl group, it's important that the methyl group is axial, or excuse me, that the methyl group is equatorial because it's stable, more stable by 1.8 kcals per mole. It's very, very important that the tert-butyl group is equatorial, because when the tert-butyl group is equatorial, it's more stable by 5.4 kcals per mole, which is a huge number. So when we have di-substituted rings, there are a couple of different relative positions that the groups can have. For example, the groups can both be cis, so they might both be on the same side. In that case, we might have axial and axial if they're 1,3, or if they're right next to each other on carbons 1 and 2, then we might have an axial and an equatorial if they're both pointed up. And so depending on the position that they have on the ring, whether it's a 1,2 disubstituted ring and the groups are right next to each other, or a 1,3 or a 1,4, the cis and trans isomers can have different relative positions of equatorial and axial. So if we look here at, this is a 1,3 disubstituted cyclohexane, which just means that one group is on carbon 1 and the other group is on carbon 3. So in this case, we have a cis 1,3 dicyclohexane because both carbons are on the same side of the ring. So this is a cis stereoisomer. So in this one, we have two different conformations. We have a diaxial conformation, which is the one on the left, and we have a diequatorial. So notice that on the left, both methyl groups are up. We have up axial on the left and up axial on the right. They're both up and they're both axial. On the right structure, the right conformation, both of those methyl groups are still pointed up, right? Up equatorial and up equatorial. The hydrogens are pointed down, the methyls are pointed up. So again, this is very, very important to remember. During a ring flip, axial becomes equatorial and equatorial becomes axial, but up stays up and down stays down. So on the left, we have a 1,3 dicyclohexane and both groups are up, and on the right we have a 1,3 dicyclohexane and both groups are up. The only thing that's happened during the chair flip is that axial has become equatorial. And when we have equatorial groups, they're far more stable than axial groups. And so in this case, if I ask you which of these conformations is more stable, you would say the diequatorial, because those big groups, the methyl groups, are equatorial, and the equatorial position has more space. If we have a trans 1,3 disubstituted cyclohexane, here one of the groups is pointed up and one of the groups is pointed down, then on the left we'd have up axial and down equatorial. And after the chair flip, the group that was axial became equatorial, and the group that was equatorial became axial. So on the left, we have one axial and one equatorial, and on the right, we have one axial and one equatorial. So they're the same energy. These happen to have one methyl group equatorial and one methyl group axial in both conformations, so they're identical. So the energy is the same in these conformations. Notice, though, that the axial group on the left is up axial, and on the right, it's up equatorial. On the left, it's down equatorial, and on the right, it's down axial. So down stays down. It just changes from equatorial to axial. If we have two groups of different sizes, so for example, now we have an ethyl group and a methyl group. Well, if we had that same situation that we just were looking at, where one group was axial and one group was equatorial, and then we do a chair flip, and we still have one axial and one equatorial, well, when they're both the same size group, like they're both methyls, then those two conformations are equal. But in this case, the groups are not the same. One group is an ethyl group, and one group is a methyl group. Well, the ethyl group is bigger, and so when we have this situation where one group is equatorial and one group is axial, there actually is a preference for the bigger group to be equatorial. So even though a methyl and an ethyl are very similar in size and very similar in their contribution to the energy of the molecule, ethyl is still bigger, so there is still a preference for the bigger group to be equatorial. So if I have a choice here where I can either on the left make the methyl equatorial or on the right make the ethyl equatorial, I choose to make the ethyl equatorial because the ethyl is bigger, the ethyl needs more space, and there's more space in the equatorial position. So that's the more stable conformation. And finally, we get back to that T-butyl group. So that T-butyl group is huge. And so the reason that, remember, when we looked at the table, methyl was 1.8, ethyl was 1.9, isopropyl was 2.1, and then suddenly T-butyl was 5.4. So T-butyl was some big jump happened between isopropyl and T-butyl. And so the reason is, look at this group at the top image here on the left, in the top left corner. That T-butyl group has a carbon that's axial, that's attached to the ring, pointing straight down, and then there's 3 CH3 groups. So when there's a methyl, those CH3 groups are all hydrogens. Those hydrogens can still get close enough to the hydrogens in the ring to cause steric hindrance. now that it's a methyl group that has its own hydrogens, it gets really, really, really close to the hydrogens in the ring. So why the difference then between isopropyl and T-butyl? Well, again, let's look at that first image in the top left corner. Imagine that methyl group that's pointing down and to the left where it says extremely crowded, and you can see that H on the methyl group is getting awfully close to those other H's that are in the ring. Imagine that whole methyl group is just a hydrogen. Well, if you replace that methyl group with a hydrogen atom, then that group now becomes isopropyl. It still has those other two methyls right underneath where it says axial. Those CH3s would still be there, but I'm saying replace that other one with an H, then that group is an isopropyl. So if that is an H, then there's in that one position, if we consider that bond is not rotating very much, the one with the isopropyl group, then that H sitting there is pretty far away from those H's, at least about as far as a methyl or ethyl, and so it would be about the same amount. So that's why isopropyl is fairly similar to methyl and ethyl in terms of its steric crowding, because we can imagine if that were an H in an isopropyl group, then maybe that during that one, if that group were not spinning too much, then that H would maybe keep a similar distance to the other hydrogens that are in the ring. But because of this tert-butyl group, there is no position that is not crowded. Every single position where that tert-butyl group tries to spin is going to be very crowded, and it's going to cause lots of steric hindrance with the other groups that are in the ring. So the tert-butyl group cannot really be axial, or rather I should say the energy difference between equatorial and axial is so great when we have a T-butyl group that the amount of conformation that has a T-butyl group axial is incredibly minuscule. So much so that we don't even really have to consider it. So much so that even though it's possible for a tert-butyl group to be axial, it is so unlikely at room temperature that we can say that 99.999999% of all of the molecules have that tert-butyl group being equatorial. So sometimes we say that a tert-butyl group locks the conformation. The conformation, if there's a tert-butyl group, it doesn't really matter how many other groups are axial, because that tert-butyl group must be equatorial. So regardless of what's going to happen to the other substituents on the ring, if we have a tert-butyl group on a ring, the most important thing to do is make that tert-butyl group equatorial, even at the expense of putting other groups axial, because that tert-butyl group is such a big group that it's worth 3 methyls in the axial position or more. So it has to be in the equatorial position, essentially. The point is, when you have T-butyl, you must make it equatorial.